So there are a few different ways that people see electron configurations. And the only way that I see it is by looking at the periodic table. I see it as part of the periodic table. The reason the periodic table is shaped this way is because of the behavior of electrons. So the periods, all the elements that are in a period, some of their electrons are all in the same energy, outermost energy level. Not all of them, but some of them. Which column they're in, they have the same orientation, like the spread of electrons in the S's and P's and D's and F's, if they're in the same column. This leads to similar behavior in how they react, what ions they form, what kind of compounds they form, if they're acidic or basic or whatever. The differences lie in the fact that as you go from one row to another, you get more protons and further away energy levels. And so that changes the, like, how reactive something is. But fluorine, chlorine, bromine, and iodine all have similar kinds of behavior. Like overall, they all gain one electron to become anions. They all form one bond with carbon if they're going to bond to carbon. They all can bond to hydrogen and form an acid. If they just bond directly to hydrogen, they'll be all acids. How reactive they are is completely different. How acidic those acids are, completely different, because of how large the atoms are. So fluorine is really tiny, iodine is really big in comparison to fluorine. Okay. So we are going to use an electron configuration table. So do not think of this as the periodic table right now. So when you look at this, only think of electrons. And so I did put the symbol in the left-hand corner of each box. And the only reason that's there is so that you can find the element that you want to find the electron configuration of. So once you find the one that you're looking for, you ignore all the other symbols and you only look at the numbers. Okay. I had this printed in color so that it kind of highlights S's and P's and D's and F's. So we're going to use this to figure out how the electrons are distributed into different sublevels. So this is not how they're organized from the nucleus out. This is just how they naturally, for the most part, fill up their sublevels. Okay. So we are going to, let me show you. I have it on a summary right here. This last page of notes, this is like a little summary of electron configurations. So the way that I suggest that you do this, you find your neutral element on the periodic table. So all the elements are on this table here. Okay. You use the sublevels that are labeled on the table to determine which ones are there. And then you write them down as you come to them. You go left to right. And then once you get to the end of the row, you go to the next row until you get to your element. And then you count over to your element and then you're done. Okay. So we're going to just start with our little practice problems down here. So we're just going to start with fluorine. And so first you have to know the symbol of fluorine so that you don't choose the wrong one. It is F, which is the first halogen right there. Okay. And so there's where fluorine is. You are going to start at the first sublevel, which is 1s. And you're going to write down energy level and sublevel. 1s. How many electrons that you're going to use is you're just going to count through over here, and you see how there's a 2 there. So a total of 2 of fluorine's electrons are in sublevel 1s. And then you're going to come down to period 2. And some of its electrons are in 2s. So you're going to write down 2s. Fluorine is on the other side. And so you're going to, since you're going to go all the way through it, you're going to put the last number, which is a 2. That's how many of its electrons. So number, energy level, sublevel, superscript. Energy level, sublevel, number of electrons. And then the last section, the last sublevel that's labeled here, that's where fluorine is. So we're going to write down 2p, which is the sublevel. And then you're going to see fluorine, and how many of its electrons are in 2p? 5. If you add up all of the electrons, it adds up to a total of 9 electrons. And fluorine has 9 electrons. Okay, so see if you can do the same thing for nickel. Find nickel on the chart, and then start at the first sublevel, which is 1s. And every time you get to a new sublevel, you'll write down the new number letter. Just work your way from left to right. You'll write down the number and letter, and then you'll see how many electrons, which is the last box in that group. If you make it to the end of a row, then you would look, since this is color coded, you will look at the last like box in the little sub-level labeled section, and that's the number of electrons that it would have. And so if you go all the way to 2p, you'll see the last number is 6. So 6 of nickel's electrons are in 2p. This is what you should have for nickel. One S2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Each number, letter, superscript is its own little piece of information. And when you write them all down, it kind of gives you a picture. It might not be in the order that it occurs in the atom, but we wrote them down based on the trends on the periodic table. So it's much easier to use the trends so that things are in the right spots. So with nickel, if you look at the numbers, anytime something has the same energy level, it's in the same energy level. So you see how this is 3s, 3p, and 3d? What energy level are all those things part of? Energy level 3. But we wrote a 4s in the middle of them. Does that mean in a nickel atom, there's a 4s in the middle of the 3rd energy level? No, no. This 4s is the 4th energy level. It just so happens for the atoms, naturally, there will be some electrons in the 4th energy level and maybe a few less in 3D. Because the d orbitals, there's 5 of them, squished in with the 3 orbitals of 3p and the 1 orbital of 3s. So it's very crowded. But 4s, empty. So it is often more stable electronically for the electrons to be in the the beginning of the fourth energy level and not completely in the 3D because of how crowded it is. Okay, that's my understanding. I kind of made it sound like, you know, they were at a party or something. But okay, how many total electrons? You just add up all the superscripts. 28. How many electrons does nickel have? 28. Okay, so now I went from the second period to the fourth period. Now we are going down to the sixth period, lead. That is PB. It does not have the normal like letter, but it's PB. It's going to be kind of long, so you might have to like write smaller, or I have to start all the way over here. So we have to work our way all the way to right there. But I want you to pay attention to right here. This is outlined in red. The lanthanum atomic number is 57. And then 58 is down here. Okay. And so every element past lanthanum is going to have some of its electrons in the sublevel 4F. So where does this section actually belong? Right here between lanthanum and hafnium. It actually goes there. Okay. When you write, see if you can write them down. There's a lot because there's 82. When you've written them all down, go back and add up all of your superscripts and make sure it adds up to 82, not 42, 82. If it doesn't, if you subtract what you got from what it should be, you might end up with a 2 or a 6 or a 10 or a 14. If you're off by one of those numbers, then you omitted either an S or a P or a D or an F sublevel. Anytime you go past where you previously had gone, you're going to find yourself writing the same thing at the beginning because all of them have the same configuration up to wherever that element is. They will not look the same because the size and shape are going to be slightly different based on the number of protons. But overall, everything past nickel is going to have this same beginning. It's just going to have a different ending. And so lead is way past nickel. And so for 3D, we're not going to stop at 3D8. We're going to fill up the D sublevel. And so if you go all the way to the end, you can see that a total of 10 of the electrons for lead are in 3D. And then right here, this is 4P. So you're going to write 4P. And we're going to go all the way to the fourth period. I mean, the sixth period, and this is just the fourth period. And so it's going to be full. So there's 6 electrons in that. And then you go down to the next set of sublevels. You have 5S, and it's full. And then 4D, and it's full. And 5P. (6S). Okay, now we get to the whole F and D thing. And so Our element is way over here, and so it has this entire 4F sublevel. How many total electrons of lead are in 4F? 14. So you're just going to write 4F, 14. And we still have to put the D electrons. So that's going to be 5D. And we're on the other side of the transition metal block. So 10 of lead's electrons. And here's where lead is. And so it's the second electron, the second one in. And so it has 2 electrons in, 6p. If you add all of those up, it should add up to be 82 electrons. So we have 226, that's 10. 262, that's 10 more, so that's 20, 30, 36, 38, 48, 50, 56, 60, 70, 80, 82. I was trying to get to multiple to 10. Okay, so 82. They're all there. What is the biggest energy level number that you see? Energy level. 6. And which ones have a 6 in front of them? 6S and 6P. That's the outermost inner. So between it, we wrote a 4F and a 5D. Are they really in between these sublevels and energy level 6? No. Where is 4F? What energy level is that part of? It's part of the 4th energy level. So 6, if you just think of layers of an onion, you can use like Shrek. So 6th energy level. 4F is part of the 4th energy level. It's 2 energy levels down. Most elements do not use this shape that we call an F wave function with a L equal 0, 1, 2, 3. Most of them don't, because it's very, very crowded. It takes something with a lot of protons and a lot of layers, a big atom, in order to actually have space to utilize little tiny spots in it for its electrons. We have a question? We're going to do a lot more of these later on. Yeah.
So we would abbreviate any of this?
Yes, we're going to do it later. We're going to do it later. Look. Okay. What I do is I like to get a overall picture in all the different ways of the electrons. And so we use the electron configuration as a really quick way to write out which sublevels all the electrons are in. If we want a picture, then we draw a diagram, and it's an orbital diagram. So diagram is a picture, and it's going to be a picture of the orbitals. But we are not going to do wave function pictures where we're going to draw like these 3-dimensional math models and try to overlap and put electrons moving in waves. We're not doing that. We're going to do boxes and arrows. So are they really boxes? No. But every box is going to represent a very complicated orbital that has a certain shape. We are just doing a really quick image, and we're going to use this. So if we draw some boxes and the boxes are empty, then that means that there are no electrons in those orbitals. If the boxes are all full, it means that there's no spots that you can make bonds. If they're almost full, then there might be spots where electrons can go. So any open spot in an orbital is a spot where an electron can go. Okay, so orbital diagram, we're actually going to do the location. So we're going to go all the way to the 4th quantum number. So in an orbital diagram, we're going to have the energy level, the sublevel, the orbital, and the actual spinning electron. Every box is going to represent one orbital. Okay. We're going to use half arrows. If you want to do an entire arrow, that's fine. I just do half arrows because they're quick and it's a half a spin. So let's do half an arrow, half a spin. Okay. The arrows represent the electron. So when you draw an electron in an orbital diagram, you're not going to use a dot, you're not going to use an E, you're going to use an arrow because you're showing how it spins. The direction of the arrow represents the spin of the electron. So this is helium. Helium only has 2 electrons, 1 S2. And so S is only 1 orbital. So go back to the summary before. S has 1 orbital, P has 3, D has 5, because that's how many quantum numbers there are. And F has 7, because there's 7 quantum numbers. There's 7 orientations of that weird shape, but wave function probability shape for F. 7 orbitals. So this is like if you look at a map key, this is the map key. So if you do an electron configuration, which you will, and you see S, 1S or 2S or 3S or 4S or 5S, and you do the orbital diagram, every time you see S, you're going to draw 1 box. If you see anything that is like 2P or 3P or 4P, you're going to draw 3 orbitals or 3 boxes because it's 3 orbitals. D, you're going to draw 5 orbitals as 5 boxes, and you want to connect them like a long rectangle. If you draw them as a bunch of single boxes, it looks like you've lined up a bunch of S orbitals. Okay, F7, 7 boxes in a big rectangle. The principles that we are going to use to fill up the orbitals, they're named after 3 different people. Pauli, from before. Okay, so Pauli exclusion principle. Where you first, no 2 electrons have the same quantum numbers. What that translates into is when you go to put the actual electrons in the orbitals, you can't have them spin in the same way. And so, since they can only go up or down, no orbital can have more than 2 electrons because there's only 2 directions. If you put 3 electrons in the same orbital, 2 of them will have the same direction. They have to have opposite spins. Okay. Hund's rule. Orbitals with the same energy, that's like they're S, P, D. Okay. They will fill with 1 electron. Of the positive 1/2 spin, with the up arrow, before you go and put a second one in there. The last one, and the reason that we use the shape we are and the way that it fills up, like we fill up energy level 1 before 2. Now, when you get to the D, it's a little bit different because they're degenerate energy levels. Energy levels fill from lowest to highest. And the sublevels also fill from lowest to highest. So S is the lowest sublevel within an energy level, and then P, and then D, and then F. So within an energy level, like within energy level 2, energy sublevel S fills up first and then P. Within energy level 3, it goes S and then P and then D. But 4S fills up before 3D. Okay, so just real quick, we're gonna do sulfur, and then after our break, then you'll just do the orbital diagrams for the 3 from before. Okay, so our example was sulfur earlier. That was 1s2, 2s2, 2p6, 3s2, 3p4. So what you do is you write down your configuration and then you look at the letter and you go up to our little P up there. You're like, okay, S. S is always a single orbital, so I'm going to draw one box. So for 1s, you're going to draw one box and you're going to label it 1s. What will you draw for 2s? You will draw another single box because every s sublevel is just one orbital. Okay, 2p. You're going to go up here and go, okay, the p sublevel is always how many orbitals? 3. And so you're going to draw 3 boxes. And then you're going to label it 2p. And then we have a 3s. Anytime it's s, s is always a single orbital. And then we have 3p. And so I've always had a hard time with rectangles and dividing them up. And then I saw a student last year do it the opposite way. And I was like, oh my gosh, that makes so much more sense. So I always drew the box first, like the rectangle, and then try to draw the inner.
Did they do the lines?
They did the lines first, and then they do the box. And I was like, oh my goodness, I've been doing this for 30 years and always had a hard time, like, especially D and F. I'm like, oh my gosh, it's not big enough. Draw the vertical lines first and then put the box around it. And it was like, oh, that was easy. So for P, after I saw her do that, I was like, oh my gosh, you're so smart. Okay, so I do like, there's 1, 2, 3. And so I got my boxes. And then I'm just going to draw the bottom and the top. And then I just felt kind of stupid because I never thought of it. Okay. Repeat. Okay. So you got all your orbitals, then you put the electrons in. You don't want to think about the electrons first, just the orbitals. And so you draw 2 arrows inside of 1s. They have to be opposite direction. Here's my advice. Draw the up arrow and then the down arrow. I do half arrows because I'm just quick. I want to do it quick. Okay. 2s, how many go in there? 2 up and down. Okay. 2p. This is the way that I want you to do this just to prevent yourself from making mistakes. You should go up, 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 and then come back and go down, down, down. Because when you're filling up the P and the D and the F, it's not always full. And if your habit is 2, 2, 2, you will get it wrong. Because it goes 1, 1, 1, and then if it doesn't fill up, then something's half full. Okay, so go 1, 1, 1 across and then come back. This is the Hund's rule. Okay, S, 3S is 2 of them. Okay, 4. Okay, this is where you go. We go 1, 2, 3. Where does the 4th one go? One of the orbitals. It doesn't matter which one. It's to get orbital. They're all just boxes on a piece of paper. They're all the same though. On this piece of paper they are. No matter where you put it, it should be 1 pair and then 2 solos. Okay. Okay.